Swayam Prabha. Digital India. Educated India.
So, welcome to the third lecture on the module rolling element bearings. After this lecture, we will start the module 7 of the design of transmission elements, and that seventh module will be the belt drive, and that will be the lecture 1 for the belt drive. So, let us start the third lecture on rolling element bearings. In our previous class, we studied about the load relationship of rolling element bearing, and we found that log of the load which acts on it and log of the life has a linear relationship, and thus we got a equation F multiplied by L to the power 1 by A is equal to constant, where A is 3 for the ball bearings and A is 10 by 3 for the roller bearings, cylindrical and tapered. And we obtained an equation which was given by this one, and it is equal to the C10, that means the dynamic load is equal to the rated load, which is also called the rated load, and the rated load is equal to the design load for which we want to select the bearing, within the bracket the design or the desired load life divided by the rated life to the power 1 by A, and in terms of life in hours, the equation is converted by using this equation. That means life in cycles or revolutions is equal to 60 multiplied by life in hours. This is life in hours multiplied by the RPM of the shaft, and so we will have this RPM, which is revolution per minute, is multiplied by 60 to get revolution per hour, okay, and then this 60 your hour and hour is cancelled, and we have the cycles, and so we have rated load is related to the desired load with the desired life and the desired RPM multiplied by 60 divided by the rated life, the desired RPM or the rated RPM multiplied by 60 to the power 1 by A. The desired design load FD and the life LD come from the problem statement, and the rated life LR will be stated by the specific bearing manufacturer. Many catalogs rate the rated life as 10 to the power 6 revolutions. The catalog load rating C10 is used to find a suitable bearing in the catalog. It is often convenient to define a dimensionless multiple of rating. That means a value of XD is taken, which is the ratio of desired life divided by the rated life. So, this X is actually a ratio of desired value to the rated value. Now, in the previous slides, we studied the force and life relationship versus life relationship, and for that case the reliability is 90%, that means the rated reliability. Now, if we want to select a bearing for reliability other than 90 degree, then that will become the desired reliability RD. Okay. So, we must have a relationship which relates the reliability to the dimensionless number x, which is L divided by L10, or L desired divided by L rated. So, a constant load and life measure distribution is found to be right skewed. That means in the normal distribution we get this type of thing, but in the at the constant load the life measure has a right skewed type of distribution. And so, the Weibull distribution is a good candidate for this type of skewed distribution. Defining the life measure in dimensionless form as x is equal to LD divided by LR or L divided by L10, because the rated life is also called the L10 life. The reliability is expressed with a Weibull distribution as per this Weibull distribution, reliability is given by e to the power minus x minus x0 divided by theta minus x0 to the power b, where x is this number and x0, theta and b are the Weibull parameters, and they are x is equal to life measure dimensionless variate L divided by L10 or L desired divided by L rated, and x0 is the guaranteed or minimum value of the variate, theta is the characteristic parameter corresponding to the 63.2121 percentile value of the variate, and b is the shape parameter that controls the skewness. So, for a particular Weibull distribution we will have a value of x0, theta and b. So, if we have a value of x, we will know the reliability. So, reliability is related to x with the help of this equation. Now, an explicit expression for the cumulative distribution function is 1 minus r from this equation, and that will be given by 1 minus the value of r taken from this equation. Now, if our design line is this one, that means we want to design our bearing or select a bearing for reliability equal to RD, and the rated reliability is 90%. So, for 90% reliability we will say the load versus life or load versus x. Earlier we were having log of the load and log of the life. Now, this is converted into dimensionless number x, where x is given by LD divided by LR, and so we have a graph log of the f versus log of the x, which is given here. So, the rated line will be the line corresponding to reliability equal to 90%, and the desired reliability line will be the line corresponding to which the reliability is RD. Okay. Now, the catalog information, the manufacturer's catalog information will be at A, the rated load and the rated life. Okay. This will be the rated life, and this A corresponds to rated load. And rated load is the dynamic load capacity, and that is C10. So, this F rated is C10. So, the manufacturer's catalog will provide you a point A, and the design point or the desired point is D, where the load which is to be which will act on the bearing is FD, and the x corresponding to this D is XD, which will be equal to your LD desired life divided by rated life. Okay. So, the design information at point D at coordinates FD and XD on the reliability curve RD is known, and we have to get this value FD. Okay. So, the designer must move from D to A via B. Let's see how. Because for a fixed reliability, we have a relationship f L to the power 1 by A is equal to constant. Okay. So, along this BD line, the constant reliability line, we can apply this equation. That means FD divided by XD, the coordinate of B is your XB and your FB. This is the coordinate of B, and coordinate of D is your XD and FD. And so, we can apply the formula on this constant reliability line, F and x to the power 1 upon A is equal to constant. So, on these two lines, it will be FB multiplied by XB to the power 1 upon A is equal to FD multiplied by XD to the power 1 upon A. And from that, we got the value of FB, the FB value corresponding to point B. And this B is the point where the FB is equal to FA, because here the coordinate is your let us say XA and your FA. These are the coordinates at the A, XA and FA. And this is the rated line, and so it becomes equal to XR and FR, rated X and the rated F. Rated F is C10, the dynamic load capacity. So, it is XR and C10. Okay. And AB line is your horizontal line, and so your FB will equal to FA. FB will equal to FA. And reliability at D is equal to reliability at B, because it is a constant reliability line. So, FB is obtained, which is given by the desired load divided by X desired divided by X at B. Now, along the constant load line AB, that means this constant load line, here the load is constant, that means FA is equal to FB. So, at constant load line, what we have, the load is constant, but we are moving from reliability 90% to reliability desired, RD. So, the value of RD is obtained from the equation of the Weibull as we determined in the previous slide. RD is equal to e to the power minus XB minus X0 divided by theta minus X0. From this equation, we got the value of XB, this value, XB. So, XB is equal to X0 plus theta minus X0 log 1 upon RD. So, for any desired reliability, the value of XB can be obtained from this equation. Okay. Knowing the value of XB, now we will use the earlier equation of constant reliability line. FB is equal to FD divided by XD divided by XB to the power 1 upon A. Now, here this will equal to XB and XD, and XB we have just derived in the previous equation, here XB. So, XB is substituted in form of X0 plus theta minus X0 log 1 divided by RD to the power 1 upon B, and this whole 1 upon A. Now, we know that FB, you see here, this was B and this was A. So, force at B is equal to force at A and it is C10. So, your FB will be the C10, the rated load. So, this FB will be substituted at C10, and if a factor of safety is taken, application factor AF is taken, so it will be equal to AF multiplied by FD and within the bracket this term. Okay. Now, RD, if desired reliability is 90%, then in this equation we will substitute RD is equal to your rated reliability 90, and you will get this equation as the earlier equation where the reliability is fixed. Okay. So, if we want a load, the dynamic load as per desired reliability, we will use this formula. So, let's how we make the selection of bearings, the rolling element bearing. Determine the value of radial load factor X and axial load factor Y. How you will determine it? Knowing the value of the radial load, knowing the value of the axial load, Fa upon Fr, which will act on the shaft, you will select a trial bearing. For the trial bearing, you will have static load capacity C0, and so you will have a value Fa upon C0, and that will give you the value of E and X and Y. The values of these factors depend upon two ratios, Fa upon Fr and Fa upon C0, where C0 is the static load capacity, and this C0 you will get from a trial bearing as per the bore of the shaft or the bore of the bearing. Then compute equivalent dynamic factor Fe from Fe is equal to Vx Fr plus Y Fa, where V is the race factor depending on whether the inner race is rotating or the outer race is rotating. After getting this, you will get the equivalent dynamic load. Now, decide the expected life of the bearing, convert the expected life in hours into millions of revolution. Then calculate the dynamic load capacity from the load life equation. Check whether the selected bearing has the required dynamic load capacity. If yes, the selected bearing is suitable for this purpose. Otherwise, change the trial bearing and repeat the process till the dynamic load capacity of the selected bearing is more than the calculated dynamic load capacity. Now, this figure shows you about the code which is used by SKF bearing for different bearings. For the your single row deep ball bearing, the number used is 6. So, if the code of the bearing starts with the number 6, then it means it is a single row deep groove ball bearing, and the code is different for different type of bearings which can be seen in this table. This is the table from where we get the value of X and Y depending on Fa upon C0 and the value of E, and this E is the Fa upon Fr. So, we will determine the ratio Fa upon Fr, where Fa is the axial load, Fa is the axial load and Fr is the radial load, and C0 is the static load capacity of the bearing, the trial bearing selected. We have other in the manufacturer's catalog, you will see this type of table where corresponding to different type of bearings, and in this table you may see that the bearing designation starts from 6. It means this is related to the single row deep groove bearing. Okay. So, this table is for single row deep groove bearing, and the principal dimensions, the inner diameter of the bearing, outer diameter of the bearing, and the axial width of the bearing is given, and also the dynamic load capacity C10 and the static load capacity C0 of a particular bearing is also given. So if suppose you have selected this particular bearing, because the bore of your shaft or the bearing is 12 bore bearing you have to select. The diameter of the shaft is 12, and so 12 bore bearing you have to select. So D corresponding to D is equal to 12 you will select. So your bearings for this bore are this set of deep groove ball bearing. So among them any one you will select as a trial bearing, and thus you will have a value of C0 and you have a value of this C10. This is the dynamic load capacity of this bearing. So the calculated value of C10 must be lesser than this, then this bearing will be appropriate. Now for other bore diameters, the tables are given for bore diameter 17, 20, 25, for bore diameter 30, 35, for bore diameter 40, 45, 50, 55, 60, the bearings are given. Okay. Now let us see one example which will make the process of selection of the ball bearing easier. So a shaft is rotating at 1440 rpm. So the rpm of the shaft is given, is supported by two bearings. The force acting on each bearing are 6000 Newton radial. So Fr is 6000 Newton radial, and the axial load acting is Fa is 3500 Newton. If the shaft diameter is D, the diameter of shaft is given as 40 mm, and so in the manufacturer's catalog you will select the bearing corresponding to bore diameter equal to 40 mm. So what you will do is, in this table you will select the bearings corresponding to 40 mm bore, these bearings. Okay, and 40 mm, and the expected life of the bearing is 500 hours. The expected life in hours, it means desired life in hours is equal to 500 hours. You can convert it into number of revolution by multiplying it by 60 and the rpm of the your shaft. Okay, then that will give you the life in revolutions. So since Fa upon Fr, that means the axial load which is acting on the shaft and the radial load which is acting is equal to 0.7, it means the component of axial load is less than 0.7 of the Fr, and we have seen in the one of our lecture that if axial load is less than 0.7 of the Fr, then we go for single row deep groove bearing. So a single row deep groove ball bearing is suitable. Let us select SKF 6208. Now how you have selected this? This is selected from this table, 40 mm bore, and we are selecting 6208, the mid value. Okay, we are not going to the top one, we are not going to the bottom one, we are selecting 6208. 6208 means the last two digit is 8, so 8 multiplied by 5 will be the bore. This 8 multiplied by 5 will be the bore, it is 40, and 626 means it is deep groove ball bearing, and 62 means 02. 0 is the width series and 2 is the diameter series. Okay, so 6208 bearing whose static load rating is 16600. 16600 is the static load rating for the selected bearing, and the C10, the dynamic load rating, is 30700. 30700 is the dynamic load rating for the selected bearing. Now, let us find the ratio Fa upon C0. This is equal to 0.2108 and corresponding value of the E from the table is obtained as this one. That means corresponding to Fa upon C0 is equal to 0.21. Fa upon C0 is equal to 0.21. 0.21 is not given. You have Fa upon C0 is equal to 0.13 and Fa upon C0 is equal to 0.25. And so, we will do the interpolation to get the value of E corresponding to our Fa upon C0, which is lying in between these two values. So, after interpolation, we get the value of E is equal to 0.3545 and Fa upon Fr is 0.5834, which is greater than E. So, our Fa upon Fr is greater than E. Fa upon Fr is greater than E. So, X and Y we will determine from this, not from this, because that is for Fa upon Fr less than or equal to E. Then from that we got the value of X 0.56 and Y is equal to 1.252 by interpolation. So, knowing this X and Y and taking the velocity factor or the race factor and taking inner race as a rotating, then V will become equal to 1. So, equivalent dynamic loads is obtained as this one. Why we have obtained equivalent dynamic load? Because there is a radial load and axial load on the bearing. So, we have to find the equivalent dynamic load or the equivalent radial load or hypothetical radial load, which is equal to Fe. So, life in millions of revolution is given by your C10 is the rated life, rated dynamic life, and that is Fe the dynamic load, and LD desired in hours, the desired revolution of the shaft multiplied by 60 divided by rated life. Rated life is 10 to the power 6 and the life desired in hours is 500. Revolution of the shaft is 1440 multiplied by 60 to the power 1 upon 3. 3 we have taken because it is a ball bearing. So, the C10, the desired value of the dynamic load is equal to this one. This is the desired value, and the bearing which we have selected 6208, for that the value of C10 is 30700. You may take this from this table. For 50, the dynamic load capacity is 30700. 30700. This is the dynamic capacity of the selected bearing, and the dynamic capacity desired is 27165.3, and so the selected bearing is suitable. Now, suppose this C10, the calculated value of C10 comes as greater than this 30700 dynamic load capacity of the selected bearing or the trial bearing, then we will again go for repeat the iteration by selecting a bearing, another bearing which have a more value of dynamic load capacity. So, what we will do is we will go for under 50 bore, this 6208 has dynamic load capacity equal to 30700. So, we will move to the bigger one where the dynamic load capacity is 41000. So, with this C0 again we will find Fa upon C0 and then you will get the value of E, then X and Y. After getting X and Y, again we will calculate the value of equivalent dynamic load Fe, and then this C10, and that C10 will be compared with the C10 of the selected bearing. Now, C10 of the selected bearing should be more than this calculated C10. Now, let us take another example in which the reliability required is other than 90%, the rated reliability. Now, in this particular case, again the revolution of the shaft is 1440 and the radial load is 6000, axial load is 3500, shaft of the shaft diameter is 40 mm and the expected life is 500 hours. But the only thing is every data is similar to the previous one, but the reliability required is now 99%. So, for that case what we will do is, again we will select a trial bearing based on the bore of the shaft or the bore of the bearing. So, bore is 40 mm. So, corresponding to 40 mm, we have selected 6308 bearing whose static load rating C0 is this one and the dynamic load rating is this one, and that for 6308 you may see, for the 6308 the static load rating is given by this and the dynamic load rating is this one and the bore is 40 corresponding to that. So, after this we found the value of Fa upon C0, that is this one, and for this Fa upon C0 which is lying between this and this, we will interpolate to get the value of E. E comes as in between this and that is 0.3308, 0.3308 in between this and this by interpolation. And we got the value of, then we will get the Fa upon Fr which is greater than E. Therefore, X is equal to 0.56 and Y is in between these two, because our Fa upon C0 is lying in between these. So, these two are again interpolated and we got the value of Y as equal to 1.35 and V is 1. And so, equivalent load Fe is obtained, which is given by this one. Now, after getting equivalent load, this Fe, which is the desired load now, that will be called the Fd in our formula. So, Xd is equal to Ld divided by Lr. Ld is obtained in terms of millions of the revolution, because life is given in number of hours. So, this formula is used and the rated life is 10 to the power 6, and so we get Xd is equal to this one. Just remember the two curves, that was the reliability rated and that is 90%, and this is the required reliability Rd. The design point is here, the A point is here and the B point is here, B. Okay. So, corresponding to this is your Xd, this is your Xb, this is your Xa, and corresponding to this is your Fd, and this is your C10. Well, C10 is the desired dynamic load capacity, F equivalent is the desired, okay, and the formula which we had just studied will be used, knowing the value of the variable parameters x0, theta and b. So, those values are given and so we got the value of C10. This R desired is your 99% or 0.99. So, C10 which we obtained is 47,022.3 Newton, and for the selected bearing 6308, the C10 is 41000 Newton. So, for the selected bearing, dynamic load capacity is lesser than the desired dynamic load capacity. This is the desired dynamic load capacity. Well, so the selected bearing is not suitable. So, we will come for the bigger bearing where the dynamic load capacity is bigger. For this 6308, dynamic load capacity is 41000. For the bearing 6408, 6408 means the bore is same for both the cases, 8 multiplied by 5, but this is 03 series, width series is 0, diameter series is 3, but here the width series is 0 and the diameter series is 4. Okay, outer diameter has increased. So with that, again the process is repeated for this. These are the values. Then we got the value of Fa upon C0, which is lying between these two. So the value of E after interpolation is in between these, so 0.89, and the value of X and Y will be in between these. This will be 0.56 because it is constant, and this comes as Y as 1.5. Okay. So there we get the value of this Fe, and this Fe will be used as a Fd in the formula of reliability. So this Fe is just taken as the Fd, and C10 is this one, Rd is equal to 0.99. So we got C10 is equal to 50,110.2, and for selected bearing 6408, the dynamic load capacity is very big in comparison to this one. It means the desired dynamic load capacity is lesser than the dynamic load capacity of the selected bearing. Hence, the SKF 6408 bearing is suitable. Now, if the combined reliability of multiple bearing on the shaft or in a gearbox is desired, then the total reliability is equal to the product of the individual reliabilities. For two bearings on a shaft, the reliability will equal to the reliability of the first bearing multiplied by reliability of the second bearing. If the bearings are to be identical, each bearing should have a reliability equal to the square root of the total desired reliability. If the bearings are not identical, their reliabilities need not be identical, so long as the total reliability is realized. So with this, we ended the selection design of the rolling element bearing, and in that particularly we studied the selection design of the ball bearing, and these are the references which were used in the in this particular module, and basically we use the SKF bearing catalog data given in that. So now we are going to start the next module of the lecture series on design of transmission elements, and that module is the belt drive, and this will be the first lecture on the belt drive. So let us start the belt drive. First of all, let us see what are the rigid and flexible drive. Now, if we see the drives which we studied till now, that is the drive through with the help of gears, there is a direct contact between the two elements, the pinion and the gear. There is metal to metal contact, and from that contact the force is transferred from driving gear to the driven gear. Okay. In flexible drives, there is an intermediate link such as belt, rope or chain between the driving and the driven shaft. So we have here a driving shaft, and here is the driven shaft. On these shafts, a driver pulley is mounted with the help of key, and the driven pulley is mounted with the help of key. Then on this pulley, an flexible element is mounted. That flexible element here is the belt. Okay. So since this link which is connecting the shafts or the driving and driven pulleys are flexible, and so this drive is called the flexible drive. In gear drives, rotary motion of the driving shaft is directly converted into rotary motion of the driven shaft by means of pinion and gear. In flexible drives, the rotary motion of the driving shaft is first converted into translatory motion of belt or chain or the rope, and then again converted into rotary motion to the driven shaft. So what actually will happen in this flexible drive is the rotary motion of the shaft is given to the rotary motion to the pulley, that means the driving pulley, and this rotary motion is converted into the rotary motion on the or of the flexible element, that is the belt. then you will get the translatory motion here, and again this translatory motion will be given to the driven pulley, and the pulley will start rotating. So translatory motion will be converted into rotary motion, and rotary motion of the driven pulley will be given to the driven shaft, and thus power will transmit from driving shaft to the driven shaft with the help of the pulley and the belt, pulley or the rope, or sprocket and the chain. Now, advantages of belt drive. Belt drives offer the following advantages compared with other types of drive. Belt drives can transmit power over considerable distance between the axes of driving and driven shaft. You may see that in the case of gear, the distance between the two shafts is this one, and that will be the radius of pitch circle radius of the pinion, pitch circle radius of the gear. But in this case, the axis between shaft is more. You may transfer power between the shafts which are far away from each other. The operation of belt drive is smooth and silent because there is no any metal to metal contact. They can transmit only a definite load which, if exceeded, will cause the belt to slip over the pulley, thus protecting the parts of the drive against overload. That means this is designed to transmit a particular load due to the friction which is acting between the belt and the pulley. Now, if the load increases, then this frictional force will be lesser in comparison to the load which it has to transfer. Then the slipping will start taking place and it will protect the drive against that overload. They have the ability to absorb the shocks and the damps vibration due to flexible connecting element. They are simple to design, they are low initial cost. There are some disadvantages also, such as belt drives have large dimensions and occupy more space. The velocity ratio is not constant due to belt slip. They impose heavy loads on shafts and bearing. There are considerable loss of power resulting in low efficiency. Belt drives have comparatively short service life. Belt drives are mainly used in electric motors, automobiles, machine tools and conveyors. Now, the belt construction. The desirable properties of belt material are as follows. The belt material should have high coefficient of friction with the pulley, because that coefficient of friction actually drives the belt and pulley, or the rotary motion of driven pulley is converted into the translatory motion of the belt, and vice versa on the driven side. The belt material should have high tensile strength to withstand belt tensions. The belt material should have high wear resistance. It should have high flexibility and low rigidity in bending in order to avoid bending stresses while passing over the pulley, because on the pulley the belts has to pass like this. There will be the bend, so it must be flexible and it must have a low rigidity in bending in order to avoid bending stresses. Belts are made of leather, canvas, rubber or rubberized fabric and synthetic materials. There are two types of flat belts, leather belt and the fabric rubber belt. Now, the belt construction, there is a specific term, ply of the belt in the belts. In order to make a practical thick belt, you want to make a practically thick belt, so it should have sufficient strength. You have to put number of layers of the leather, or the fabric arrangement must be there in the case of fabric rubber belt. So these layers are called the ply. Belts are specified according to the number of layers or plies. For example, single ply, double ply, triple ply. In the case of leather belt, if 3 layers are there, then it will be called triple layer. Similarly, in the case of fabric rubber belt, if 3 layers are there, then it will be called triple ply belt. The power rating of the belt is also specified per ply of belt. For example, the power rating of Dunlop high speed belt is 0.0118 kilowatt per ply per mm width of the belt. Fabric rubber belts are made from several layers of canvas or cotton. B. This is the figure B. There will be fabric and the rubber. The fabric transmits major portion of the load and increases the coefficient of friction. It is due to the presence of rubber that different plies of fabrics are binded by the rubber. Fabric rubber belts are widely used. Advantages: they have high load carrying capacity, they have long operating speeds of up to 300 meter per second. Shown in this figure, the type 1 is called the raw edge belt. The edges edge belt, it consists of plies of fabric cut to the width of the belt. There are between the plies there will be layer of rubbers. The edges of the fabric are protected along the edges. The raw edge belts are flexible, therefore they are widely used for high. The second type is called the layer by layer. Layer folded edge means one layer is made like this, the another is covering the first one. The third enclosing like this, wrapped around with rectangular plies. Such belts may or may not have rubber layer, spirally wrapped. You see, the spirally wrapped are there. This type okay, they are made of a single piece of fabric without any rubber layer in between. Compared with raw edge belts, layer by layer and spirally wrapped folded edge belts have edges of semicircular shape, which is advantageous for operation on pulleys having flanges, for cross belt drives, and where belts are to be shifted. Now, the ends of the belts are joined by methods as illustrated in this figure 3. There are 3 methods: cementing, lacing, and by using metal fastener. These are the metal fasteners which are used to connect the edges or join the edges. Now, the cemented joints leather belts are cemented with a tapered lap joint or of length of 20 to 25 times the belt thickness. Multiple ply belts are cemented in the form of stepped joints, like this is the first, then second and third, like that. The strength of cemented joint is 80 to 85% of the strength of the belt. Laced joints is done with catgut or with raw hide strips, okay, like this joining. The strength of the laced joint is 50% of the strength of the belt. The strength here is lesser. In the case of first one, the strength is up to 85% of the belt. The third one is with the metal fasteners. joints with metal fasteners require least time to make the joint. However, they are not suitable for high speed operation due to the metallic connections made. The strength of screwed or hinged joint is 25% of the strength of the belt. This is the cross section of a V belt. These were the flat belt where cross section of the belt was like this. Now the cross section of the belt is something like this. Okay. In between is the load carrying cords, and this is the cover, and in between is the rubber. So V belts are made of polyester fabric and cords with rubber reinforcement. The cross section of the V belt is shown in this figure 4. V belts consist of following 3 parts: the central load carrying layer, layers of polyester, cords or polyester fabric, which are located on horizontal lines near the center of gravity of the belt cross section. They are in the central location. The surrounding layer of rubber to transmit force from cords to side walls, and outer polychloroprene impregnated elastic cover, which will be just a cover which binds all these two. The layer of the rubber located above the load carrying cord, means this one, is subjected to tension and called the tension layer. So this layer will be the tension layer. Similarly, the layer of rubber below the central cord is subjected to compression, and thus they are called compression layers. The polyester cords or fabric transmit force from the driving pulleys to the driven pulley, which in turn transmit power. Since they are located near the neutral axis of the cross section of the belt, the stresses due to bending when they move along the pulley, they will bend. But the central cord is in the central location along the neutral axis. So along the neutral axis, we know that bending stresses are 0. So since they are located near the neutral axis of the cross section of the belt, the stresses due to bending of the belt around the pulley are negligible. Now there are 2 types of belt construction, open and crossed, as illustrated in figure 5 and figure 6. In this figure 5, we have this driving pulley, and this is the driven pulley, the bigger one, and a belt is wrapped all around it. Green color is the belt. Okay. So if this type of thing is there, then it is called the open type belt drive. Now in this case, you see the belt is crossed. Just see the green colored, which is the belt. Now it is moving in this way, and then it is wrapped on the driven pulley. Then again it is crossing, moving like this. So if this type of arrangement is there, then it is called the closed belt drive. Now the angle of wrap, the belt is tangent at point C on the driven pulley, and it is at E at the driven pulley. So C and E are the points of start and end of the contact of belt with the driven pulley. So the angle formed by that on the center is this angle of wrap by the bigger pulley, alpha B. Similarly, the angle of wrap on the smaller pulley is given by this alpha s. Now, you see what will be the angle of a wrap for the case of cross belt? It is this one, and when you will compare, you will get that this alpha b is bigger than this alpha b. Similarly, alpha, the angle of wrap at the smaller pulley alpha s for the case of crossed belt is bigger than the alpha s for the case of open belt. Okay. The distance between the axis of rotation of the shaft or the pulley is given by this c, and the diameter of the bigger pulley is capital D, diameter of the smaller pulley is small d. Now, the difference between these two constructions is as follows. An open belt drive is a belt drive in which belt proceeds from the top of one pulley to the top of another without crossing. The crossed belt drive is a belt drive in which the belt proceeds from the top of one pulley to the bottom of another and crossed over itself. In both cases, driving and driven shafts are parallel. In an open belt drive, both driving and driven pulleys rotate in same direction. In the cross belt drive, driving and driven pulley rotates in the opposite direction, and that is clear here. In the open belt, the driving pulley is rotating in a clockwise direction and the driven pulley is also rotating in a clockwise direction. But in the case of cross belt, if the driving pulley is rotating in a anti-clockwise direction, then the driven pulley will rotate in a clockwise direction. So, rotation will be different in the cross belt and same in the open belt. In cross belt drive, the angle of wrap is more, therefore power transmitting capacity of a cross belt drive is more than that of an open belt drive. In cross belt drive, the belt rubs against each other because it is crossing each other. While crossing, also the belt has to bend in two different planes. These two factors increase the wear and reduce the life of the belt. The open belt drives, when the center distance is more, the belt whips, that is, vibrates in a direction perpendicular to the direction of motion. When the center distance is small, the belt slips increases. Both these factors limit the use of an open belt drive. Then also the cross belt drive do not have these limitations. The open belt drive, irrespective of some disadvantages, are more popular than the cross belt drive. In the open belt drive, the length of the belt is determined from this formula, where C is the center distance of the shaft and the two shafts, and small d is the diameter of small pulley, capital D is the diameter of the big pulley, alpha b is the angle of wrap of the bigger pulley, and alpha s is the angle of wrap of the smaller pulley. Similarly, for the case of cross belt, the length of the belt is obtained from this formula. Now, these are the references which were used in this lecture 1 of the belt drive. So, in this lecture which was the first lecture for the case of belt drive, we studied the details about these flexible drive, and we studied the construction detail, the joining details, and the two types of belt drives which are used, that means the open belt drive and the closed belt drive. And we also found the equations to determine the length of belt for the case of open belt and closed belt. Thank you.